of our online series entitled Understanding and Exploring Network Epidemiology in the Time of Coronavirus. Last week, we kicked off the series with an excellent tutorial by Laurent Aubert-Dufresne from UVM. And before I introduce today's speaker, let me give you a little preview to what's coming up. Next week, we have Sam Scarpino from Northeastern University. And the following week, we have Ginestra Bianconi from Queen Mary University of London. In these difficult times, a bright spot for some of us is that society has gained a newfound appreciation for mathematical modeling and data analysis. This series has a particular take on those efforts for COVID-19. That is, we think about how can we apply network science to understanding disease spreading patterns. And so last week we heard the first part of a tutorial, which is Introduction to Network Epidemiology, and we'll have another tutorial today introducing us to more elements in network epidemiology. I just want to remind you that this series is brought to you by the Combine program at UMD. Combine stands for Computation and Mathematics for Biological Networks. And it's in partnership with the Vermont Complex Systems Center. We'd love for you to stay connected. For those of you who weren't able to attend the session last week, you can view it on our YouTube channel. You can get to our YouTube channel and other materials related to these events from our website, combine.umd.edu. We also have the slides from today's speaker posted there. So if you want to go back, if you want to download those and go back and follow along, if you missed something, please feel free to do that. We also invite you to follow us on Twitter using hashtag net_COVID, or you can follow Juniper Lovato, one of our co-organizers, or me at Gervin Michelle. And I want to encourage you to ask questions. This worked really well last time. You can both ask and answer questions in the chat window. Our facilitators will be monitoring the chat and bring your questions up to the speaker primarily at the end of the presentation. I should let you know that Zoom has some features that are security features that you can't just paste a link into chat, I believe. So just so you know that. And so with that, I'm really delighted to introduce today's speaker, YY Ahn. YY is a professor in the School of Informatics, Computing, and Engineering at Indiana University. He did his PhD at KAIST, which was formerly called the Korean Advanced Institute of Science and Technology. After his PhD, he went to Northeastern University for a postdoc. Following that, he was a visiting researcher at Dana-Farber Cancer Institute. He's done some great high-profile research combining network science and data science, and he has a particular knack for elegant visualizations. And so I'm really delighted he was able to join, and he's going to be able to give us this tutorial today. So with that, I'm going to turn it over to YY.
Thank you very much for kind introduction. This is YY and my study here. I'll share the slides. So yeah, my name is YY. I work at CNET, Center for Complex Networks and Systems Research, and uni at the Lodi School of Informatics, Computing, and Engineering. And you can reach me through my email here, and then yeah, you can mention me on Twitter at YY. So I'd like to first thank all the organizers, including Michelle and Juniper and everyone. And I think this is especially meaningful nowadays because this social distancing really kind of obstruct the flow of ideas between us. And I think that's why it's so great to have this kind of event where we can share ideas and kind of enhance the flow of ideas across disciplines. Okay, so, and also I would like to thank Laurent and other speakers. I know that they are super busy working at the front line of the disease. Yeah. Okay, so here are today's questions I want to talk about. The first question is like, why now? Why now? Like, why is it happening right now? And then we want to talk about the network science aspect of it. Laurent covered a lot of it, but I would like to show a little bit different perspectives too. And I want to talk about what makes it really difficult to measure something and model the epidemic. And also, I want to briefly touch on like why it is difficult to prepare or kind of respond to the epidemic. And then finally, I want to close with some thoughts on like what do we do? How can we address this current pandemic? So in a short film produced by Box in 2015, they asked Bill Gates, like, what are you most afraid of? And Bill Gates was talking about the pandemic, like this COVID-19 pandemic. And this is another quote by Melinda Gates. And she's saying that this is not a once in a century pandemic, as some people mentioned it. And she said, we'll absolutely have more of this. So in other words, this is really serious pandemic, but at the same time, they are expecting more. And I think that's the consensus of many epidemiologists. And there are many reasons to that. The first reason is the population growth and urbanization. In epidemiology, I think there's a really nice analogy between fire and epidemic. In other words, the population is like a fuel to the pathogens and epidemic diseases, infectious diseases. And if you have a small segregated populations, even if there is a big severe outbreak, it will just die out because they cannot jump to the other population. But if you have a large enough population where we keep adding new fuel to it, and that span the whole world, then we'll see much fiercer, more explosive and recurring outbreaks. So this is a kind of measurement of influenza infections. And it's like a clockwork. It goes to the southern hemisphere, it comes back to the northern hemisphere. It keeps recurring. And that's why, that's because we have this large connected population that span the whole world. So it's impossible to really eliminate like things like flu. And it's not just about the human population, it's also about animal population. Because of factory farming, we have high density of animals, and it's particularly dangerous in terms of disease spreading. This high population means there is a weaker evolutionary pressure against disease's severity. So in other words, like think about avian influenza. If there are a lot of chickens living in like really close quarters, then even like really severe version of severe types of avian influenza can sweep through the whole population, which will not occur in like natural environment. So yeah, and also there are more and more clash between humans and wildlife because we keep removing like forest and habitats for wildlife. So that means there is a more contact between human population and the animal population. And that means there are more and more pathogens coming from animals to the humans. So here's a very nice documentary produced by Netflix and Vox, and it's called Explained. It's actually a series of documentaries. And one of them is called The Next Pandemic. And it's a really nice watch. And they show this plot of number of disease outbreaks and which fraction of those are zoonotic, which means like coming from the animal. And as you can see, we are seeing the increasing number of zoonotic diseases jumping into human population, and then makes it much more dangerous in terms of pandemic risk. And if it sounds familiar, yeah, and because it happened before. The writer, Arno Carlen, had a really nice book called Man and Microbes, talking about the history of all these epidemics and pandemics. And here, they were saying that agriculture brought humans so many new pathogens that it seems wondrous they survived. And actually, most of the infectious disease we are dealing with, like measles, cold, influenza, they are more or less souvenir species that we acquired through agriculture. So this is a kind of bad combination, like more population, animals, more disease. And we can also see from this chart, which is of course like previous, the pandemic. Yeah. And now the whole world is really well connected, right? Due to the high mobility and all the airline networks. And that's another reason why this is, there are more and more risk for pandemic. So if you compare like the spreading of Black Death with SARS, in Black Death case, you can see the wavefront of the disease moving through the continent. But in SARS, you don't see any clear pattern, right? Because they are all connected through the airline network. So the scary thing is you can reach the most populous cities in the world within a day. That means if something happens in some part of the world, it will reach most of the countries within a few days. So all these factors contribute to higher risk of really serious pandemic, and they will not go away anytime soon. So I think that's why it's so important to think about all this pandemic risk right now, because right now is the kind of all things getting mature and more increasing that all these factors are increasing the risk of the pandemic. Okay, so next question is, why should we think about the network structure? I'll refer to this plot again. The planes are not just randomly traveling across the world. They follow a specific routes, and they can be captured by the network structure. So in other words, network is a really natural framework to capture this macroscopic mobility structure. And you can also see the network structure of like commuting patterns if you go down the scale. So like really global scale, like country scale, and all this macro mobility is captured by network. And also if you look like microscopically, network is also a nice way to capture the context structure. So on the left, you can see some of the data collected by the Social Patterns project. And they use these small devices, like sometimes Bluetooth devices, to capture face-to-face interactions among a population, small population. And then on the right, there's a really nice study by Sune Lehmann's group at DTU. And they could, they give out like 1,000 mobile phones to the college students. And then they could monitor how they gather and make these social connections to each other. And by looking at like really microscopic, like high resolution data, they could see all this nice context structure forming between people. So as such, like we can use the network to really capture this microscopic context structure. And it makes sense that all these microscopic contexts form these networks. Or you can think of like more meso-scopic structure. So in this work, Duncan, Peter, they formulate this hierarchical metapopulation model. And then they show that there will be many resurgent epidemics in this type of population structure. So I would argue that when we talk about network epidemiology, I think it's less about how can we use network for epidemic modeling, but it's more about when can we safely ignore the network structure. So I want to kind of flip that notion a little bit. Like for instance, say you are just looking at one city and the epidemic is spreading without much like kind of intervention. And in that case, the SIR model may be all you need. There are numerous examples where you can see a nice fit of SIR model to this kind of data. But if you consider like this type of question, like for instance, I want to model how the disease spread in a school or hospital, and you really want to see microscopic spreading pattern, then you probably want to get a hold on this type of data, like microscopic context network structure data, because that's what captures the spreading pathways. Or if you want to forecast how things will spread across the world, then again, you probably want to pay attention to this network structure formed by worldwide airline network. And I would like to mention a really nice study by Dirk Broekman and Dirk Helbing, published in Science several years ago. So here they wanted to see how much network matters in like global scale pandemic scenario. So in this graph, they used the geographic distance to see whether there is a relationship between distance from the origin and then the number of days it takes to kind of import the case from the other countries or the origin. So in the case of H1N1 or SARS, you can see that there is almost no correlation, right? Between the distance and how long it takes to import the case. But you can define an effective distance using the airline network. So if two countries have a lot of traffic, airline traffic, then they are effectively close together because they are well connected. So if you measure this effective distance and plot the same thing, it shows like this. So remarkably, if you measure effective distance and then the days until you import the case, it line up really nicely. And actually what they did after that is they constructed the kind of tree representation from the origin and then all other airports in the world based on this effective distance, and then run the simulations of the epidemic starting from the origin. And as you can see that there is a really nice ring structure propagating through this tree, although there is no clear pattern in the map. So what it tells us is that the network is what really capture the spreading pathways in the global scale. And that's the kind of the main idea behind one of the most kind of, how to say, state-of-the-art model right now called metapopulation model. So the idea is, let's just keep the macro structure, like worldwide airline network, and ignore all the details below that. Let's just assume each city is just a well-mixed solution governed by the mass action principle, and we just run SIR model. But we connect those populations to each other through the transportation network. And this model works really well in kind of forecasting and simulating disease spreading across the world. So here's this project, the GLEAM project by Alessandro Vespignani's group. And it incorporates this macro mobility structure by looking at the small cells. So you have a country like US, and you divide this into small census cells, and then you incorporate commuting and airport airline network into that. And then you also use the population data from census to model the population structure of a given cell. And for that, you use this age contact matrix. Like given your age, what's the contact pattern with the other age groups? And this can be thought of as kind of first approximation from like well-mixed solution to more kind of network-based contact network. So it's not like actual network structure, but you are modeling it as a kind of age groups. Yeah, so metapopulation models are kind of most complex and advanced model you can think of. So the point here is like things should be really simple as possible, but no simpler, as Einstein put it. So it's very important when you model epidemic spreading, you need to decide what need to be incorporated, what are the essential elements, and what can be ignored based on your question. So in metapopulation model, the essential ingredient is this macro transportation structure, and you are ignoring kind of microscopic context structure. Okay, so another really important topic is the heterogeneity. And Laurent already covered this topic, but I want to kind of reiterate because I think this is probably the most important takeaway from the tutorial. So if you forget everything, but if you really understand this particular lesson, then I think it'll be a success. So here's a question. So pick a bunch of random people and put it in group A. And at the same time, ask each of them to name a random friend and put those random friends in group B. And here's a question. So on average, group A and group B should have about the same number of friends or not. So you can use the Zoom's feature, like yes or no, to vote. So if you think group A and group B should be about the same, have about the same number of friends, you can say yes. If not, you can say no. Can you vote? Okay, it seems like most people get this point. Okay, yeah, so there are more no, which is very nice. Yeah, so let's walk through. So assume a network, but we are thinking about like random case. And that means we are just breaking apart all the edges, actual edges. And we are thinking about this random structure. So we only care about the degree of the nodes. And every node has a edge stop, not actual edges, okay? And in this case, if you follow an edge to get a random friend, that can be thought of as kind of picking a random edge stuff from the population. Okay, you line all of the nodes up on the right side, and then you pick one of them, one of the edge stuff randomly. And if you think about it, here node 1 has 3 edge stuff, and node 2 has only 1 edge stuff. So that means 1 is 3 times more likely to be picked. And that means when you sample through the edge, you're sampling preferentially based on the degree. And that's the basis of the French paradox. In group A, the random population, everyone is sampled based on just the degree distribution. But in group B, the random friends population, people get sampled by K times PK. So high degree nodes are sampled more. And easy way to understand this is thinking about an extreme example where there is one node connected to everyone and everyone is only connected to that node. And that means if you randomly sample from this network, you'll sample all the periphery. But if you ask everyone to name one of their friends, it'll be all the center star node. And that really illustrates the problem. Okay, here's another question. Again, you can answer with yes or no. Assume a random network now, where you construct this network by grabbing each pair of nodes and connect them or not based on a fixed probability P. P is non-zero but much smaller than 1. The question is, will this network exhibit the friendship paradox? Okay, I think it's about half and half. Yeah, so I think about half of the respondent think yes and half no. The answer is yes. The exact same reasoning works as long as there is a non-zero degree variance. So as long as there are different degrees present, the same thing happens. So it's not only about scale-free network or network with huge degree variance. As long as you have degree variance, this effect is there. Although it can be very small, but it's still there. And whatever network you can think of, French paradox is there. Okay, another question. So assume now, think about disease spreading context now. So assume that disease is spreading on a kind of static contact network and assume large variance in the degree distribution. And now it's very early stage of the outbreak. And we know who are infected in the network, and we sample from those impacted individuals. And if you examine their degrees and calculate the average degree, would that average larger than the average degree of the whole network? Again, yeah, yes or no. Okay, I think there are more yeses. Yeah, and this is exactly the same problem with the French paradox. Again, French paradox, we are sampling nodes by following an edge, right? I'm picking a random friend. And if you think about disease spreading, it's the same thing. So when someone gets the disease and spreads through other people, you are sampling the edge to arrive to a newly infected people. And that means the exact same logic is in play. and the degrees of the newly infected people will be higher than the average degree of the network. So in other words, if you have a network with a high degree variance, with the nodes with like really high degree, they are preferentially attacked by the disease from the early stage. And there was a really nice paper in Physical Review Letters in 2004. And they measured, they simulate the spreading of the disease, and they measured what's the degree of the infected nodes. And as you can see, at the beginning of the spreading, all the hubs are preferentially attacked. And then as time goes by, the degree of the newly infected nodes goes down and approach the average degree of the whole network. So there is this phenomenon of hierarchical spreading. So if something is spreading through a network, if it's static, you'll see all the hubs kind of attacked first. And like in like a COVID case, you may expect to see kind of celebrities or politicians or people dealing with many people, meeting many people. They tend to be attacked first. Or also you can think of like bus drivers, like doctors and nurses. They may be attacked first because they are in the position where they interact with many people. So it also kind of provides an explanation why these big cities and big countries tend to get hit first. There are two factors in play, well, more than two factors, but the most important factors are proximity to the epicenter, measured by kind of effective distance. But at the same time, there is a preferential spreading. So if you are well connected in the global airline network, you are probably likely to be attacked first. Although the outcome will largely depend on how that particular city or country react and responded. But at the same time, there is a kind of preferential attack to the high degree places. So then question is like, when the disease will stop, or when can we stop an epidemic? What's the condition that we can stop the epidemic, right? So like here's a little bit different formulation of the previous tutorials. In the previous tutorial, Laurent deal with this question, but here is a slightly different formulation. So let's assume that we color the edges that will transmit the disease. So let's say we know the future and we know that these edges will transmit the disease. And we use fixed probability T to color all the edges with red, okay? And an SIR model can be kind of approximated with this picture by thinking about pick a random node from this network and kind of pull it out. And you pull all the nodes connected through those red colored edges. And that's like a spreading of disease across the network. Okay, so it's a kind of nice way to think about the disease spreading. And by doing so, you make connection between SIR model and the bone population problem from physics. So let's think about it. So it's like when you sample a node by following an edge, we are wondering like how many extra infection do you create? So I'm impacting one of my neighbors. And the question is how many extra infection will this neighbor will create? And what do you call this quantity, by the way? Can you answer in the chat? Yeah, so you can calculate this way. So let me go through this. So T is, yeah. So here is a KPK term. So you're arriving a node with degree K, and that probability is proportional to KPK, right? And then KPK sum over K is the normalization term for that probability. And we are multiplying K minus 1 because one of the edge is used for transmitting the digits, right? So you have K minus 1 edges left. And then if you multiply T, then that gives us like how many extra infection will it create, right? And if you sum over that for all possible K, then you get this formula. And as many of you answered in the chat, this is called I'll note. But the thing is, I'll note equal 1 is the epidemic threshold, right? And if you calculate the critical transmission probability T, TC, the form looks like this. And then this particular term, K square, the average of K square, this is a problematic term because it diverges in scale-free networks. And as you have more and more degree variance in the distribution, this goes up and TC decreases. So in other words, if you have the static network with a huge degree variance, it's really, really difficult to block an epidemic happening in the network. Yeah. And in English, you can say that because it's a combination of two factors. One is the disease will hit the hubs preferentially. And the second one is the hubs will spread to many, many others because they have so many connections. So this combination of these two factors means that it will be really, really difficult to control the spreading of the disease, right? So yeah, that sucks. But you may wonder, like, how about the metapopulation model? Like here, we are completely ignoring all the microscopic context structure, right? But here now we have the structure of the macroscopic contact, like airline network, come into play. And here was a nice paper by Vittoria Colliccia and Alessandro Besniani, who has been pioneering the metapopulation model. And they derived this formula. And here again, there is a term of K squared plus 2 zeta average. And that term, again, come into play. That's like a variance in the degree distribution of the global airline network. So there are many factors like travel rate, like what's the subpopulation size, what's the recovery rate, and all these factors. But at the same time, again, it becomes pretty hard if there are big hubs in the global airline network. Yeah, this term. So you may ask, okay, that sucks, but is there any hope? So there are interesting studies that kind of flip the coin. The thing is, the other side of the coin of this vulnerability is that if we can protect the hubs, then we can do much better than assuming no heterogeneity, no network structure. So it's all about, it's now becoming all about the hubs. So for instance, we can take the approach that let's really protect the hubs. So one realistic solution can be Let's protect and immunize all the workers in healthcare, grocery, public transit, delivery, all these workers who meet and contact many people that we kind of know of. But there is another really interesting answer from network science, but it may not be super practical. Can you kind of guess based on what we discussed about? So the question is how to protect or immunize the hubs in our network. Yeah. So some people mentioned acquaintance immunization. Yeah. So here is an interesting possibility. Pick random people and immunize not those ones, but their random contacts. It's like a flip the coin using the French paradox. So by doing that, by not picking the random population, but their acquaintances, we can better identify the hubs, even if we don't know the network structure. And there was a really nice paper on this topic. So here, x-axis is a degree exponent, assuming scale-free network structure. So you can just look at one vertical line. And y-axis is a fraction that needs to be immunized to block an epidemic. And here, there are two immunization strategies. One is random immunization. And you can see that when exponent is about, like, say, between 2 and 2.5, you need to immunize everyone, really, to get the herd immunity. But if you do this acquaintance immunization, like randomly selecting people and then not immunizing those, but their contacts, acquaintances, then you can do much, much better. So by immunizing only like 20 to 40% of the population, you can still block the epidemic in the population because they attack these immunization strategies, identify the hubs very effectively. So it's called acquaintance immunization. And another interesting possibility of using that principle is using kind of social sensor, creating social sensors. So in this work by Christakis and Fowler, they kind of created the two groups, group A and group B, as I mentioned, in like Harvard dormitory, I think. So you sample random people and ask them to name friends, and you compare these two groups. And then you do a flu influenza surveillance on these two groups. And it turns out that this friend group get the flu first because they are in the more central location of the network. So these are like interesting possibility of like kind of using the French paradox on our advantage. So here's a quick summary about the implication of network structure. So I would argue that it's a really natural way to capture context structure across scale from microscopic to macroscopic. But depending on your question, your model may work fine, even without incorporating the network structure. Also, again, I reiterate Lohong's point that network allows us to incorporate heterogeneity in the structure into the model. And this can produce like totally different phenomenon from non-network models. And it become all about the hubs and this degree variance and existence of hubs is a curse, but potentially can be a blessing to address diseases, infectious diseases. Okay, let's talk about the second topic, the next topic, which is measuring and modeling an epidemic, or why counting is so hard. And basically the theme is this, the data ruins everything. You may recognize this map. This map is produced by Dr. John Snow in England during one of the really bad cholera outbreak in London. And he was the first one to go and count and put that count on the map of the cholera kind of victims in a location. And using this map, he could identify the well was the problem. And that was kind of one of the really important evidence that support the germ theory. So it's a really historical map. And it tells you like how important it is to be able to count and just put that into a visualization. So yeah, we want to make a tracker. We want to show this counts, right? So how hard should it be, right? We have all the data sets, like number of cases. We have all the data set about like number of deaths across the world. And we can, using that, we can measure like fatality rate. And that will tell us like how dangerous this disease is, right? So, and you can get the data easily, just press the button and you get the CSV files and you can start plotting, right? And yeah, the first thing you want to do, maybe we know from the last tutorial that things grow exponentially because the new cases is depending on like how many current active cases we have, right? So it should be exponential. And that means if you use log scale in Y scale, it will be a straight line, right? So let's try that. And you realize that the timing is really different across different countries, right? So you can do something like this. You can kind of collapse everything by kind of identifying a point where things start to take off. And a popular method, for instance, adopted by Financial Times, is a days since X number of cases. Like, okay, how many days have passed since 100 case or 10th death, right? This shows nicely how many countries are kind of following the same pattern and growing sometimes exponentially, sometimes sub-exponentially. Right? But you can kind of tweak that and learn a lot by kind of changing the parameter. But why should it be 100 cases or 10 cases? And by changing it, you can see a very different picture, like how different countries behave at different stage. So just illustration. So by the way, all these visualizations are created in observablehq.com. And that means you can go there, fork the visualization, you can edit as you want, and you can play with it. And you can even suggest me like, oh, here's a improvement you made. Can you accept the change? And I can just click and accept all these improvements. Okay, so you can create those visualizations, that's fine. But you want to ask, how accurate is this data? Like, how people confirm the cases? What does it mean to have 100,000 cases? And the thing is, in many, many places across the world, this has been happening. Say, oh, I'm really sick and I get all the symptoms. I want to get tested. You call the hospital. And then they said, oh, we don't have enough testing capacity. You should call us if you get really sick and cannot stay at home. And that means all the cases that were kind of mild will not be counted into the confirmed cases. And that means the number of confirmed cases is highly dependent on the number of tests available and how easy it is to test, right? In South Korea, there are way more tests than confirmed cases. That means the number is more likely to be accurate. But in Italy, it's not like that. And also there is a complication, like which test are you talking about? There are so many different tests. There are different types of tests, and for each type of test, there are different products, and they may all have different error rate. Like for instance, let's say you got negative from a test. That's good news, right? Like what do you think the false negative rate is? Let's say you get the negative, and what would be the probability that is false? If you can vote yes if the negative rate is less than 10%. So that means 90% accurate. Okay, I think there are more yeses. Oh, okay, about even. So I dig up some papers and found that, surprisingly, the false negative rate goes up to 40%. And especially as days go by, it can shoot up to more than 60%. So the fact that you get negative doesn't mean that you don't have COVID-19. And that these tests are really not very accurate. Also, if you look at how the test is done, it requires putting the swab really deep, and that's not easy to do accurately, and that also contributes to the false negative rate. But you may wonder, what number of deaths should be fairly accurate, right? So that means if we have some estimate of the infection fatality rate, which is number of deaths divided by number of infected, but we don't know the number of infected, but there are some estimate of this value. Then we can measure the case fatality rate, which is number of deaths by number of confirmed. And if number of deaths is accurate, and if you have a good idea of infection fatality rate, then we can kind of estimate number of confirmed, right? And that was the idea that why I created this visualization of case fatality rate, to kind of see how much underestimation is going on. So for instance, in Italy, the case fatality rate is 12.8%, which is super high. And that means there is likely at least 10 times more cases than reported, right? But the thing is, counting is really hard, and even counting deaths is not easy. The problem is there are many people just dying before getting tested, and there are people dying at home, which doesn't get counted. And UK, yeah, they haven't like really counting any deaths outside the hospital. Yeah, things like that. So there are a lot of issues with counting the deaths. And there were great books like Sorting Things Out, or this paper like Counting Things and People. Like counting requires classification, and classification is difficult. So there are a lot of non-trivial issues here. Like, okay, someone with a pre-existing condition died. Is this person died with COVID-19 or died because of COVID-19? And do we only look at like pneumonia type of deaths? Or do we consider like deaths by organ failure, sepsis, or heart attack, all these different deaths? Like for instance, there was a report that there's a spike in cardiac arrest that is likely caused by COVID-19, but because they are not like a typical death, they may not be counted as a COVID-19 death. And so there are suggestions that we need to look at the excess deaths. And that's actually how the flu death is estimated. So you have a baseline, like seasonal baseline of how many people die usually around that time. And then you can count how many excess deaths has happened. And like preliminary results seem to show that there are a lot of deaths, excess deaths in UK, for instance, than the official COVID deaths count. But here is another like tricky problem. Like if you just look at the excess deaths, that may be misleading because because of the social distancing, there are fewer deaths due to other causes. So you need to account for that too. And also there was a kind of this pictures circulated on Twitter that, oh, actually the pneumonia deaths is lower this year in US. And there is actually a big dip. But it turns out that there's always counting delay, and it takes time to really count all the cases. So we are dealing with all this undercounting, classification problem, and then delays all at the same time. So the real world is really messy, and we should be aware of all these issues. So another question is, okay, let's do the mass testing. Okay, pick a population, test everyone, and that's the way to measure the infection fatality rate and how many people actually got the disease, right? So there was some claim that the case fatality rate should be as low as 0.37%, which is really low. And then like 15% of the entire population has been infected. So that's like really good news. But the thing is, this type of antibody tests seems to have a lot of false positives. In other words, they cannot like distinguish between like this COVID-19, like SARS-CoV-2 versus other types of cold viruses. So the accuracy of this is still in question. And as you can kind of see, there's no ground truth. So it's really hard to test the accuracy of the test. Yeah. So that's the issue. And at the same time, things are more complicated than people may think, because this is a virus that's constantly evolving. So this is a kind of sequence, like a phylogeny of all the samples that was taken across the world. As you can see, there is a bunch of light blue, like China subtypes. And then you can see how they are spread through Europe and other places. So we are dealing with like constantly evolving, potentially with the varying kind of severity of the disease. So these all kind of these factors makes it really hard to measure and model the disease. So although data is useful, you should keep in mind that we are probably severely undercounting the cases. And it's really hard to measure the correct amount of cases. And not only that, we are probably undercounting deaths too, because of all the difficulties. And you should also be aware that the test is not as accurate as you may think. In other words, like knowing the current situation is really difficult. And I want to briefly talk about like why it's so difficult to respond to the pandemic. And I think this CNN interview with Bill Gates captured nicely. So the anchor asked, oh, there are states we don't need 100 cases. You're saying that even in those states should lock down, shut down. And Bill Gates was like, come on. Yeah, it's exponential growth. If you don't shut down, it grows 33% per day. That means within a week, there'll be like multiple doubling events. And it will be 100, 200,000, 100,000, like very quickly. The point is, exponential growth is really hard to grasp. And most of the disaster we are dealing with, they are more linear. The amount of resource you need, amount of damage it causes, grow linearly, not exponentially. But the infectious disease, because it multiply all the resources requirement and all the harm it does, grows exponentially. But it's really hard to grasp. In other words, if you just delay a few days, that require way, way more resources, and it will easily double or triple the number of deaths, the amount of damage it causes. Yeah. And also, like in many places, the quick reaction is, oh, we need to shut down, right? We shut down all the travels, all the people from these epicenters. Let's block the travel from Europe. But it's not so easy because again, it's a really densely connected network and it's really hard to block the traffic across countries because it severely damages the economy too. That means the whole world is more or less in the same boat. And that's why it's so important to help others so that they can mitigate the disease. Because if there is a big outbreak in another country, it will come to us. So it's not just our problem, like it's the whole world problem at the same time. And Besniani's group has been keep showing that the travel restriction is not really effective. It can delay the spreading a little bit, but it will eventually succumb to the spreading power of the disease. And given the damage it caused, given the economic damage, it's not really worth it. And also because it's not so frequent, it's still rare, it's really hard to prepare. You cannot really convince the government, it's really hard to convince government to prepare for some pandemic that may not come in 20 years, for 20 years. And South Korea is one of the countries that respond the best to the epidemic. One of the reasons was that it was hit by MERS like really hard just several years ago. And that prepared for them for the next pandemic. And also because of the exponential growth, any success in blocking the epidemic will look like an overreaction. Because again, it's just a matter of a few days. And if you've done well, it looked like you overreacted. So that's like a real challenge in like human psychology in terms of like reacting to the pandemic. And finally, I want to quickly mention the social aspect of it. Like, although infection is a biological phenomenon, an epidemic is deeply social. What I'm saying is, like poor people hit harder by the epidemic. They tend to serve in the essential work. That means they cannot really do social distancing. They tend to live in urban areas where the density is larger. And they tend to have more underlying health conditions. So all these factors like compound each other, and it really make it difficult for poor population. Yeah, so all this map shows different risk factors, like how many people are living with grandparents, things like that. And on top of it, there's this political divide happening, like Republican party members tend to be less worried about the epidemic, and they tend to do less social distancing, for instance. So what I want to say is it's really complicated to study the epidemic's impact on the population, because all these social factors come into play, like who will get it, who will die. Like in many, many states, like Black population, for instance, is disproportionately dying due to the COVID-19 because of all these factors that you can think of. So yeah, final remark, what should we do? Obviously, we need better data and models, like an estimation of the actual cases to inform policies, not only policies, but like all these forecasting models. If your model rely on this poor data, your forecasting is garbage in, garbage out, right? So we need to keep thinking about like how can we get better data. And at the same time, I think we are doing a poor job at communicating the limitations of the data to the public too. I think these are like really basic things we need to do. And second, I think all the success stories, especially in Asia, involve mass testing, a lot of testing, and contact tracing. And I think these are some of the best weapons we have, and we should implement them. And especially, there are a lot of promise of the digital contact tracing, and that can be the way to go. Okay, so I think now it's your turn. I think many of you, the participants, are creating nice projects, and I think I'll be looking forward to all the progress that will be made out of this series. Okay, thank you very much.
Thanks so much, YY. I think we have time for just a couple questions before we have to move to our next session, but that was a great talk, really hitting on a lot of the different issues with biases and before, modeling before and after outbreaks. So for those of you who have questions, if you could repeat them in the chat window and we can bring them up to YY. I know there was a question about asking about modeling, incorporating differences in race. Have you seen any modeling like that so far? I think we have a group that's undertaking that, but I know that you've been really following a lot of this recent research.
Yeah, I don't know. I think there may be some models, but I haven't seen it. I know that Sam Scarpino has been working on like poverty and epidemic in the past, and probably he's working on the same issues. Yeah, so I think that will be really, really great contribution, like incorporating different race and how epidemic disproportionately attack those populations.
All right, and I have one more question for you. Can you comment a little bit about the challenges in biases in the data in capturing it during the second wave, not just on the front where the epidemic starts to spread, but afterwards, what we'll be facing soon?
Yeah, that's a great question. I think most models are predicting the second wave. And I think what we can learn from the first wave really can make difference. Like for instance, how can we expand the testing capacity, right? So, I mean, it will reveal many more cases, and it may make the second wave look much more severe than it actually is, because underestimation of the first wave. But still, I think it's very important to rebuild kind of the actual cases as much as possible. And probably many countries will be more ready for second wave, and we can probably get better data for the second wave, I think.
Great. Well, thank you again for this really informative and thought-provoking tutorial. That's all for our first session of today.